April 9th, 2023. We're talking about the path integral. The path integral is for these position and momentum operators, P and Q, determining what would be the integral of the path is so covered by the passage of these particles that are waves. That are waves after some theory of potentials and wave resonance duality. Get back to what we call our particle wave duality. We got these Heisenberg pictures of linear particles, but not knowing their positional momentum because it works out in the quantum description that the statistical ensemble adds up. The stochastic model well represents what results. The detectional particles, when they propagate in the sense that the waves of quantum particles and in these expanding waves, or as the front of the waves, is as superclassical in the sense that the entire object's region increases as if either side of the object were even growing away from each other faster than C, or that otherwise it is super classical in that sense, that it's modern classical where light speed is a finite constant, which it is, that it results then that the flux of light being tachyonic on down from the speed of infinity, and the flux of these particles, largely the electron from electron physics, bradyonic for the light's tachyonic, less than, slower than, versus faster than, tachyonic, that the path integral, it results is for a formalism about how to add up these things that would be the sum of histories of what would be the course of passage as what results. The entire impulse of what's detected is a particle when it's caught or trapped or captured, that is observed or sampled and measured at the detector where it's detected, that the energy in this wave that so coalesces, which is this notion of something beating as due, or drawing to a point, a contraction that coalesces into the particle, was as of the travel about this arc of all the possible histories that from the superposition of states what the particle lives in our model, according to Heisenberg and Schrodinger and Pauli and Dirac, and Born and Oppenheimer say, and I'm learning about, that this picture is these pictures of what is a model of what classically then we can establish as experiments, that then when we see repeated the experiments of the dual slit experiment, which is a usual example, that the wave of what's only captured as a particle because of the ultraviolet catastrophe in electron physics and Rayleigh and the ultraviolet catastrophe, why this discrete amount of energy is as what so results that the wave packet of a photon has to have a given fixed amount of energy, or that the electron has a fixed amount of energy. Electrons are discrete in terms of fine structure constant, I imagine, or how electrons interact. That the repeated experiment results that it appears that the particles interact with each other as if they had been as of the passage of waves, that what's drawn in this pointillism of the discrete about the particle and the wave in the discrete and the continuous, which is this quantized mechanics of the continuum mechanics in terms of distinct events, a result that it behaves as if it was a wave over time. And so the reading is that the wave theory of the particle wave must be true, and the particle theory of the particle wave must be true. Whereas over the course of the theory of light and its development in Fizeau and Fresnel and Huygens and and Newton, and then for electron physics like with Millikan, and then for Rayleigh, and then for Einstein, and as examples of people's about the fringe, as it were, of light, and about caustics of light in the fringe. Then there's why this path integral is worked up to figure out how to describe how it works up that energy is transferred in the quantum regime, so that then it results that when there's a fundamental stochastic development, what results that on the averages or the means, that power and similar quantities can be described in terms of configuration services, as we've been talking about in Mogan, and the current or flow of here photons or electron holes across an area adds up from these test particles and Lienard-Wishart potentials, or the wave packet formalism of light about these solitons, the instantons, in the acoustic model of lights, acoustic models of propagation, wave propagation, that for the photons, there's the phonons, and these kinds of things, that all these particles, what's called the particle zoo, is wave interactions. After wave mechanics, what's a continuum mechanics, that's the quantum mechanics. That so establishes that according to this experiment, what we can see or what we can detect, the observables, admit that otherwise the theory without the backing mechanism of a real wave function collapse was entirely built in the statistical ensemble and the statistical interpretation. Copenhagen, that they call it after a conference in Copenhagen where it's got together and the world's physicists decided that it would be this way. That then when we talk again about Bohm and de Broglie, who are early on in this kind of development laid out and laid forth these ideas of the real wave collapse, which kind of even follows something like, earlier history, like Descartes and the theory of vortices. And I mentioned these, and I'll harp on these a little bit more, that once again, antiquity is turned over, and pretty much anything that was put down back then and picked up again, and then put down again as that an opinion was made, a decision was made to trade tractability for completeness, then it comes back the same kind of thing. So that then when we get talking about stuff like Newton's laws of gravity, or the law of gravity, an inverse squared vis-a-vis proportional to the product of masses. That as well, then there's Fadio and Lesage, which for about 150 years was the next leading thinkers' arrival at what is the mechanism of gravity. Instead of two massy bodies constantly working their eternity, always gravitating each other, and that similarly where we have a finite terms according to the ultraviolet catastrophe, so we can find something to add up and figure out how we can figure out what are discrete quantities that add up to a finite amount, and in terms of higher order terms like area or areal terms for the line, or the particle, or the volumetric terms, that these are accommodations that, as was stated, trade completeness for tractability. And thus that as the theory gets bigger and better and brighter and is supposed to take care of all these things and be more fundamental and less of the defined vis-a-vis what arrives at the derived, that is kind of so. So it's somewhere here under this stack of books, and what I've just kind of piled together here is that, well, these are kind of just some of these books. This is talking about this. These is basically like, these days the book bags are rather great, and it's kind of a hassle to carry around all these heavy books, but this is basically a year's course in mathematics that's from like the 50s or 60s. So this has got something like, it's out of Dugway, Utah. Now, what is Dugway? When you hear about Dugway, well, you think about the Dugway Proving Ground, but that's a different story. So this is published in the 1958. It's the reprinted 8th edition. And he talks about Titchmarsh and theory of functions. We've been talking about function theory and algebra and arithmetic and operators, and that's about it. sets and partitions in our descriptive set theory. And so this is a book on functions of a complex variable. I was really going to kind of look at that. This is going to help explain the Gaussian. And then this next book is Surplus Library of Congress Duplicate. All right. The Schwartz function and its applications. This is actually from the Karras Mathematical Monographs. These other things are Oliver and Boyd. So this Oliver and Boyd is different than the Karras Mathematical Monographs. So the Schwartz function and its applications gets into operator calculus. In the operator calculus, you got the Schwartz functions. Here, for example, they have this distorted image of the Vitruvian Man. There he is. It's kind of, as how you'd say, translated in the affine, where you can define what is something that preserves. It results that there's a shape between that shape in the sphere, or that shape in the circle, or that shape in the square, and that shape in the cube. That results that there's a mapping or isomorphism or homomorphism that results then that it preserves angles under the mapping. It preserves distances under the mapping. And so this operator calculus is the idea that it preserves relations under these mappings. And so then when you've established that a certain property holds for a certain regime, or where something is closed, like an arithmetic as about a vector space, or an algebra as about a vector space, this is very geometric, of course. That results then that the affine and the non-affine, and works up for translation, rotation, skew, and inversion, and this kind of thing in a usual algebra of geometric operations that can be built and closed for areas. Has that then for analysis that operator theory works up and about and over arithmetic and algebra and makes it easy to do things. For example, this book mentions conjugate coordinates in the plane, which are basically plane coordinates plus minus plus minus. They add up one to the other side of them being the identities and this kind of thing. Differential geometry, conformal maps. Conformal maps is what we were looking for with respect to what takes a projection and an array of something in a coordinate space into the same coordinate space according to this conformal mapping backwards and forwards. And usually it's considered that there's an inverse to that there's an inverse conformal mapping. But it can vary according to if the act of taking the operator actually does something. Like, for example, when we're talking about the measurement, sampling, and observer effects, that the act of actually hitting the detector is a change of state and a change of phase. And so it results that it's non-abelian, that it does not have the commutative property, it does not have an inverse. It's irreversible. So that gets in this. Oh, and he mentions Dirichlet, the Dirichlet problem, Schwartz functions, the Schwartz function and the Dirichlet problem, page 149. Now, skipping ahead a bit, because these functions have lots of applications, and they kind of fit under special functions of a sort, and as to where they're not elementary. But 149, I'm interested in what is the Dirichlet problem, because we've been talking about Dirichlet box principle and the Dirichlet function. By the Dirichlet problem, or first boundary value problem in two dimensions, is meant the following. Given a region B in the xy plane and given a function u z star defined for the boundary points z star of B, find a function uz which is harmonic in B, i.e. satisfies delta u equals 0 at interior points of B, and for which the limit as z goes to z star, u of z equals u of z star in some sense. For the purpose of this essay, we limit ourselves to a region B whose boundary is an analytic curve with Schwartz function sz, and where the boundary function of u z star is continuous. The solution of the Dirichlet problem is well known where B is a circle, absolute value z less than r. Radius, here r for radius. It is u sub t equals 1 over 2 pi. Integral for absolute value z equals r. Z is usually the argument. in the complex analysis. R squared minus absolute value t squared over quantity z minus t absolute quantity squared. U z d theta. Short calculation follows. Can be written in a form, the real part, that ut equals the real part of 1 over 2 pi I, this and that. So with a lot of preliminaries in the Gaussian, in the complex analysis, in the conventions of the Gaussian, and about why we have to differentiate the complex plane that is the Argand from the Gaussian complex plane that is the Wessel, and this kind of thing, and in terms of how that establishes that there's identities and properties that so carry, and then as we get into this in terms of these functions and families of functions that are usually parameterized by integers, like the first Bernoulli function, the second Bernoulli function, or Stirling function of the first kind, for its given arguments, or the Stirling functions of the first and second kind with regards to their first and second arguments. That these parameterize what result these functions that live in the world of special functions that end up having all kinds of numerical identities that they build and so satisfy. So that for something along the lines of the binomial and the Pascal's triangle, that it works out that that's the product of that many monomials, and it computes the coefficients inside, and there's their integers. These are the kinds of things that also are sometimes talked about in terms of recurrence relations and generators. These are hard things to figure out that basically involve the definition of a recurrence relation. And it's kind of like a differential function and the solutions of differential functions about real value variables, and that those have things to do here as we're talking about, and their fundamentals. And then also that the recurrence relations are in integers, and then they're so defined kind of like Fibonacci's number, where the nth term is the sum of the previous n minus 1th and n minus 2nd term with given initial terms. So recurrence relations in the umbral calculus of Giancarlo Rota, and this kind of thing has a very continuous or discrete to continuous metaphor, just like discrete distributions and continuous distributions, or discrete particles and continuous waves, or discrete waves and continuous resonances, harmonics, and brackets and intervals and points on either side. So anyways, this is a book that goes quite into detail, lots of things that get into why then these result, that then when having this tables of these formulas allows them to be built up together and work out mathematical methods that back in 1958 would have made it possible to, in some reasonable amount of time, work that out in pencil and paper, where at the time they did not have the embarrassment of riches of computing resources that, according to Moore's law, over the past 30 or 40 years, has made it so that an average person in their watch or their phone has about 1,000 or 1,000,000 times the CPU processing and the memory RAM that were available to these high-level scientists and mathematicians of times past. Now, and for what they say about idle hands and that the devil finds works for idle hands, that's something to keep in mind. But here the point is that anything that really ends up being better on pencil and paper for a person is also better for a computer to do it. The algorithm is more elegant. The computation is more refined. The intermediate terms are so interpolated that this is why all these special functions are as much more powerful, if applied correctly, in the days of modern computing world than general purpose. Oh, I've got 1,000,000,000, trillion, zillion neural nets, and I can just kind of let it flow together and watch what it drops out. Well, this million-eyed clock cat, with regards to the clock that's in the shape of a cat, and as its tail wags back and forth like a pendulum clock, its eyes swing back and forth, it is following the red dot. This is basically my analogy of what a lot of these neural nets are. They're indeterministic, subject to effects like gimbal lock and all sorts of things that would make them not able to predict and compute values. Though with respect to a lot of things that are often worked out under the mean, it just so happens that the exceptions are rare, and then that it just works out that there's this, as we talked about, kind of a trade-off of tractability for completeness. It's similar like so, because a general purpose implementation is dirt cheap, and it doesn't take an education to apply it. But it's like statistics in the hands of people who misinterpret statistics. I'm not sure what the word is actually. Statistics. I only arrive at Mark Twain's, there are lies, damn lies, and statistics. Where the numbers are what's relevant. We got to have the numbers, and this is called the quantitative vis-a-vis the qualitative. All these sorts of methods were integral to the solutions of all sorts of problems that these days would serve just as well in an analytic milieu of a computer algebra system, but they don't, because it's a different kind of world. But it would be better. So then this next book is Vector Algebra, Vector Methods. So the vector methods is about the vector calculus. He talks about the osculating plane, Frenet's formula, curvature. And so this has a lot of things that, again, it gets into means and methods and solutions, like polia, or how to solve a problem, or setups. I mean, how do you make a setup of all these kinds of things? And then what tools are there available? It's like, well, I don't know if we have an analytical method, but according to this, 5,000-year-old theorem of geometry, you just kind of plug it in together and draw this curve as so, according to as taut the string is that you've connected to these 2 points, and it makes your ellipse. Or the idea that the tautochrone is as simple as you can make one out of cardboard and some wheels and some thumbtacks, and you end up computing via the natural application of the experimental setup, which is gravity, in the terrestrial frame. That these are the kinds of things, kind of like the surface acoustic wave convolver that we've been talking about in Mogan, which is a device, is a lot like the vacuum tubes, and the way that they solve systems of equations automatically by their behavior, that the pentodes and the tetrodes and the triodes and this kind of thing, way up and above transistor logic of the triode, in their behavior, make it so that they're analog computers. And so what good might be an analog computer, you might ask? Well, an analog computer can, given that it can be designed and derived and implemented in silico as a special case, can solve things that would take regular algorithms in regular transistors a million years. And even when you hear about quantum computers these days, a lot of these are just using analog computers that are implemented quite generally. And also there's that analog computers are based on these methods of solutions, and according to the setups and according to the frameworks. They're very cool. And once you have one put together, it's opaque. There's analog inputs and analog outputs, and there's, for example, nothing to do with floating point arithmetic necessarily, or any other representations of numbers that fail. Most of the neural net algorithms are implemented in floating point numbers and don't necessarily have much going on in the way of avoiding what's called gimbal lock and this kind of thing. But you can always just reboot it. That gets into the joke about the engineer and the physicist and the software programmer have to test a new car that they're somehow responsible for. And so they drive up this mountain, and then as they're driving down, the brakes go out, and they careen about and around and down, and perhaps they get one of those runway ramps and make it so that they don't all die by driving off a cliff because the brakes are out. And so the physicist starts off and he's like, well, as far as I can tell, the momentum we gained is coming down the hill according to this gradient, and this incline in gravity made it so that whatever the power of the brake's fading, it was able to hold it up. And the engineer says, well, I imagine these brakes heated up and started fading because as the brakes heat up, they fade because the coefficient of static, what is that called? Friction between the brake pads and the discs, or the drums and the wheels and the hubs just gave up and out because of brake fade. And the computer programmer's like, I just am not quite sure if I could repro this yet. Maybe if we could replicate it, if we just kind of push it back up again and then try it again. This is why software engineers have it so easy, because by and large it's not a scientific profession. It's not necessarily a scientific profession. It can be, and of course, electrical engineers and computer engineers is a much different field than programming and computer science. It is one unified field, and you can call it computer engineering. That's that. So, let's see here. So then there's all kinds of methods in the vectors, and these days in the course it's usually, after linear algebra, there's quite a bit of course in establishment of vector spaces and the objects in a vector space. And we've talked about before the inner and outer products, scalar and vector products, wedge products, and then bilinear relations and symmetries, and these things to do with after that there's a vector space and it has a basis, and it has an orthogonal vector basis, and it has an orthonormal vector basis. We often, for R3, R cubed, we call this E0, E1, and E2, or E1, E2, and E3. And that's basically the Euclidean space with an origin. So that otherwise Euclidean space is just kind of a free space of otherwise undifferentiated, 3 dimensions. But within it lives this vector space, and any given point, any one is the origin, and then that affects us about coordinates are basically where the coordinate reflects these relative rates with respect to any of these 2 axes. And all of analysis is built up about coordinate analysis. Then when we talk about the coordinate free, that then that just gets with regards to like the parallel transport and the ways that then it works out that in these transformation products that it's not coordinate free in the sense that you don't have to keep track of coordinates because it's all defined by the metric and this and that in Euclidean space and this and that. It's just that in the methods it's way up above that, so then coordinates become another free, as it were, area. Then when you have terms of systems of coordinates that are not just translated among each other, like polar and Cartesian coordinates, but even differing in terms of not maintaining the affine, violating invariance or symmetry, being quasi-invariant, that these are these kinds of things that happen. And so that's a little bit about the coordinate setting and the coordinate free. So he talks about scalar, that any vector can be multiplied as scalar, vectors can be added. You basically add 2 vectors by appending the tail of one vector to the head of the next vector, and then connecting the tail of the unconnected to the head that's unconnected and calling that a vector. And that any vector can be multiplied by a scalar, and there's a distribution product, there's an associative law, and that these various laws work up why the vector product, and then there's vector product, the cross product. We talked about this a bit in the difference between a vector product and a wedge product and an outer product generally, in terms of whether it has a matrix representation in any of these inner and outer products, where the inner products represent a lowering the dimension, the outer products represent a broadening of the dimension. Whether that's appending them, whether that's multiplying them, is left outward. That's underdefined, but it's still that all these inner and outer products are defined as so. That here these are plane products, and that the cross product happens to be a plane product that preserve a given orthogonality. It represents at once a minimization in one direction and a maximization in another. The application of 2 together vis-a-vis their sum or their product. That the sum and product are, as we've been talking about, the additive or multiplicative, which in algebra are defined in terms of each other. That there's also algebras of arithmetics where addition is one thing and division is another. And it happens they coincide as a plane product or even as an inner product sometimes when the operators work out how they're closed and assembled. But there are outer products, for example, or the degenerate, where in these complex or degenerate, there's the inner and outer, respectively, or reversibly, as it were, that result all these different kinds of combinations, having all the full complexity, detail, and as well as simplicity and the directness of why things are and how it's so. My favorite mental exercises when I was a little kid were these ones like, use a process of elimination. Mr. A, B, and C, and D live on this road, and A has a dog, and C drives a car, and D smokes a pipe, and E is dot, dot, dot. And given these few conditions, draw out a matrix or grid, and then work out algorithms to fill in the points and lines until you can cross out so you can solve all these questions that follow. So it's kind of like a Sudoku or something like that, or anything else that admits a unique solution vis-a-vis finding out what's left what you would have to know in terms of then answering unknowns in dependent and independent variables. So this is a book on vector algebra, and so that's part of the Oliver and Boyd. And then this other one's Functions of a Complex Variable with Applications. This is from the same guy. Somehow I've acquired this piece of his library. Bangor, Maine, October 1956. Functions of a complex variable. And so that functions of a complex variable will be really relevant when he gets into the Gaussian and how that is. So he talks about residues, he talks about Liouville's theorem, and Taylor's theorem, and Laurent's theorem. Analytic continuation. Analytic continuation is a big thing that we have out of Swanson and the Path Integral book. And then he starts to talk about the meromorphic functions. Now, the meromorphic provides a way to get about when something's to do with the origin and the multiplicative or dividing by zero you can't divide by zero. And so the meromorphic is a way of kind of turning the setup around so that then you can do the analysis over what would be that hump, because it is if you approach that hump and it also happened to coincide that its coordinates were zero, that it would blow up. So these are these kinds of things. The maximum modulus principle. Maximum modulus principle. So yeah, he builds the definition of complex numbers, talks about the Argand diagram, functions, regular functions, conjugate functions, geometrical, some special Moebius transformations. Moebius is really fantastic, and people heard about that in Richmond, I think, a lot of times. Like, you take a strip of paper and you give it a half twist, and you tape the ends together. So you draw a line, and because it goes around that one twist, the line will eventually meet. There's only one side to the Moebius strip. There are two sides if you go around, but the one side is interpolated to follow across to the other side. It's a twist. There are no knots, K-N-O-T, knots. There are no knots in 4 dimensions. In 3 dimensions, there are knots. If you can tie a knot in a string, and if you pull the ends of the string taut, the knot will close, and there will be a knot in the string. In 4 dimensions, if you pull the ends apart, there are no knots. I don't know exactly why that is or what it means. But when we talk about the Moebius strip, and that if you take a piece of paper, a strip of paper, and you twist it one half, and then you tape those two pieces together, and you, without lifting the pen or pencil, draw a line all the way down the strip, it arrives back at the beginning, and it's covered both sides of the strip. One way to look at that is that the half turn has basically made it so that it reflects that it draws on the inside and the outside, but it just turned over. Instead of that, usually in drawing it forward, you're always smoothing in front of you that half strip. You never like stop and then turn around and start drawing where you left off, without lifting a pencil. Then after the Moebius strip, and that no knots exist in 4 dimensions, and then there's a book called Flatland, which everybody knows about, which is like, we're polygons and we live in flatland, and someday a higher dimensional figure came down and all we could see was its outline, And we learned there was a higher dimension. It's called flatland, I imagine. And then there's the Klein bottle. So a Klein bottle is a space in 3 dimensions. It's like a vase, and it has a neck, and the neck enters it and comes back around as its bottom as the same side. So essentially, the Klein bottle also only has one side for any given path you trace. You can always, without crossing that path, arrive at the end of the line. And you can draw infinitely many lines right next to it that also don't cross and also meet. And if you observe the other side, there's a mark for the same line on the other side, because at any given point has an opposite side, but it's the paths that go around. Paths. So that's a brief mention of the Moebius strip and this kind of thing. What are usual enrichments provided to people, because then they are highly contrived, but very interesting. So yeah, the Moebius strip, no knots in 3D. There's the cross product only exists in dimensions 3 and 7 for R3 and R7. It doesn't exist in other ones. Knots don't exist in 4 dimensions. These are some of the other features that get into why then when we're talking about the paths and the connectedness and this sort of thing, that again, these models of the path integral get into reasons why the models sometimes are like this, that they go all the way around. And that's why it builds up stochastic behavior. Everything in mathematics is related. Mathematics is this giant museum. David Hilbert was the guy, and he was named, for him is named the Hilbert program, and the Hilbert program is to formalize all mathematics. And shortly after it came out, and he has a list of 20 problems, and usually solving one of Hilbert's problems gets you a prize, is that then mathematics came up with Kurt Gödel's incompleteness, and it was like, nope, can never fulfill the Hilbert program. But in Hilbert's infinite living museum of mathematics is all of mathematics. So, various screw theorems. So, the complex conjugate numbers. This complex integral calculus then builds up about the contour integral and a lot of the other preliminaries that are the same in this 1958 book as the 2020 book. They're the same. Oh, and residues. I wanted to learn about residues. And then there's the topology work, and so topology is another neat and interesting and useful thing. And I found some cards here that I've collected. And in this topology book, it talks about simplicial complexes, homotopy. There's topological spaces, and continuity and Euclidean, and continuity and metric spaces. I'm curious what he says about that. Continuity and metric spaces. The definition depends essentially on the idea of distance. Continuous transformation from one metric space to another is defined by a direct generalization of the definition of continuous transformations of subsets of Euclidean spaces, point sets. This is where the elements of the space in the set theoretic, the usual descriptive set theoretic milieu, is of points. And so a surface is defined by a collection of points, whereas in geometry it's defined by constructions. Like a circle is given a point, all the points that happen to be at a given radius from that. Now that's essentially the same thing as a point set, but it's really only defined by the classical construction, because otherwise they're arbitrary, non-measurable point sets. They don't have analytical character, or what they do is not contrived to have a finite value. Whereas something like the radius of the circle has already computation. Its circumference or area or other derived quantities given those parameters. Yeah, I had something in mind about the Moebius strip and the Klein bottle, and that I just thought of, but maybe that'll come up a little bit later. because it's not usual so often to take too much time worrying about the Moebius strip and the Klein bottle and this kind of thing. But they're contrived surfaces that have this thing. Oh, I know what it was. There's a theorem in topology called the hairy ball theorem. And so if you imagine a tennis ball or otherwise like one of those plushy things or like one of those squash balls with all the little plastic threads, the idea is that if you tried to comb it, there'd be at least one cowlick on it. Meaning like a cowlick is where the curl of the hair sticks the other way. And so the idea is, though, that if you and this was where when we were talking about striating the Klein bottle or otherwise drawing a bunch of paths around it, that you could make all these non-crossing paths and it would cover both sides, whereas you never have to lift the pencil. You could draw basically a spiral as about the whole thing and fill up its area, or get approximately as close to that. Whether or not that emits a singular point, whether or not that the hairy ball theorem is true. So there's an idea that you don't necessarily have a cowlick, because when you consider a degenerate case, like, well, what if you just spin it around like Coriolis forces spin around the globe? Then only at the North and South Pole, there's nothing. And so these are point discontinuities or something like that. So that was the idea, that there's the Moebius strip, the Klein bottle, and then we can talk about the difference between those having opposite sides of surfaces and paths that connect points in the surfaces. This is why there's only one surface that can still have opposites. In terms of topology, that the Moebius strip has a half turn, and the Klein bottle has one inversion, or where you can where two of its surfaces combined otherwise would be separable. These are the kinds of things that get into then the yes, no, maybe, or the inner and outer products of the degenerate and detailed we've been talking about, or I just made up, that provide a space in the vocabulary that then we can make a table of all these things and have what does and doesn't belong to each of these areas. And that's part of a dialectic, is for everything its place, and a place for everything. So, and this other one is more functions of complex variable, topology, real analysis. That would have been a usual year of mathematics to study these books. And there's some more about in these theories about like tensor calculus, volume and integral, classical mechanics, special functions of mathematical physics and chemistry. Again, for special functions, you go to the DLMF from NIST, data science section, Digital Library of Mathematical Functions, or the Abramowitz and Stegan Handbook of Mathematical Functions. You can also find many of them as detailed in Eric Weisstein's Math Encyclopedia, that's now part of Wolfram Mathematica, and these kinds of things. The vector calculus, all right? So anyways, we're almost back to the path integral book, and then here's Morgan. This is really what kind of began this whole reading kick, was that Morgan has put together at least some nonlinear methods. So even as far back in the 70s, everything since then is pretty far behind. This is a Bosch automotive handbook, and what's an automotive handbook, you might wonder? Well, if you've ever wanted to know quite a bit about the operation of the mechanics of an automobile, this book is about the most self-contained description of all the systems that are involved in what's called an internal combustion passenger vehicle, or vehicle. So it talks about basic principles, quantities and units, conversion of units, vibration, mechanics, strength of materials, acoustics, heat, electrical engineering, electronics, sensors, actuators, electrical machines, technical optics. About gasoline motors, dieseling, about the sparks, about these kinds of things that go into a description, a milieu, a domain of all these things to do with the drivetrain, transmission control, braking systems for passenger cars and light utility vehicles, braking systems for commercial vehicles, lighting, signaling and theft deterrent devices, window cleaners. Yeah, this got it all. It really does have everything. And then the authors are kind of in these quantities and units: vibration, oscillation, electronics, actuators, mathematics, tribology, where, that's something, motor vehicle dynamics with handling. After they invented the McLaren strut and some of the other things to do with the front end of handling and about camber and all this kind of stuff in vehicles and put it everywhere, motor vehicle deaths decreased sharply because control of the vehicles was much, much better. Mechanically, not by any control inputs, just that mechanically it was more natural for the human driver. So, this is a great little book to have because it's got all kinds of stuff to do if you ever want to be a mechanical engineer in the vehicle world. All right, so here's this primer of real functions. This is another one that's from this Karas Mathematical Monographs, and this I enjoy this Ralph P. Boas. It's got a primer of real functions, but it really gets pretty high level. Sets of real numbers, continuous functions, Bayer's theorem, sets of measure zero, infinitely differentiable functions. This is pretty low level, and meaning in the sense that it builds the fundamental formulas and fundamental theorems that arises from a common, unified, and shared, entirely open, and as far as possible constructive theory of real functions as of point sets and sets of real numbers, and this standard development. So this is largely the standard development, and it gets into the theory of continuous functions and functions that are differentiable, and then functions that are differentiable a given number of times before they're undifferentiable, and functions that's called c to the infinity, which is functions that are the class of continuous functions that is infinitely differentiable. That these emit particular properties that then in these systems of operator theory and transformation products, for examples, just that they fit the mold, that their form is their function, and their function is their form. These are the kinds of things that make mathematics tractable and also complete. About where those represent the uniqueness theorems of that completeness of the theory is being done. So that's again, that would just be a usual part of an undergraduate mathematics degree. So back to Swanson, where we left off was talking about sum of histories. And we had gotten into the section sum of histories, and then chapter 3 was going to start, because I wasn't going to read about the Riemann-Lebesgue lemma, that we talk about limit as t goes to infinity of sine alpha t as a distribution, that it equals dt of d of dt sine alpha t equals 1/2 a, that we got a linearization, we got what's called a small angle approximation. And so the linearization of the small angle approximation is a very widely used thing, and it bothers me. And what it is that is sine, as x goes to 0, that it just so happens that sine 0 goes to 0. In these functions where the sine and cosine also happen to tend each other as orthogonal functions, there's this idea that the linearization of the small angle approximation, it's not without its conditions. And so that's why when it's too also that it's kind of, it erases a whole working milieu or a slog or a bog that would require all tracking through all kinds of methods to work around that, but it's still not free analysis. It's still not, it's but a contrivance, it's but a conceit. And so this linearization, which has that linearizations are a word for approximations that happen to be so in the limiting case that they so bound, not without their conditions, and if ignored in the development and not carried out as part of the development, this function is provided as long as you also maintain these conditions, like for statistics and this kind of stuff we were talking about, the damn lies. If those unstated assumptions aren't carried in, it won't be carried out. Which agrees with that result, show that the limit of t goes to infinity of cosine alpha t equals 0. This is as where he says that results that as a distribution, limit as t goes to infinity of ei alpha t equals pi I alpha delta alpha, which vanishes when integrated against a well-behaved function. So that kind of, it expresses a sentiment. In this sense, paths with infinite values for the action will not contribute to the path integral. There's basically a floor, this Planck floor or whatever. Paths with infinite values for the action will not contribute to the path integral. There's that only paths with finite action will contribute to the path integral, and it's not all the contributions. The infinite values in this sense just reflect stuff that falls off the clock or the dial or is otherwise uncomputable. They might have finite values. These remarks serve to draw attention to the major difficulty in generalizing the path integral to a sum over histories, and that is the question on precisely how the sum is to be formed or defined in a sensible way. The idea of summing or integrating over paths can be made mathematically rigorous only by the formal definition of a path measure on the space of all paths. See, when he says only, we sometimes we've been talking this in a reading of path integral about matters of style. It's clear, it's obvious, it's easy, it must, it's necessary. Here this is a only. The only establishes that also I've established a uniqueness result, that there's no other thing than this in about all these things. So when he's talking about a sensible way, we've been talking about the sensible and fungible and tractable. So here, when he says sensible, I think he means sensible and fungible and tractable, where the intuitive by itself is kind of sensible, it's just not fungible or tractable. And similarly, something that's sensible and fungible is like, this is sensible and fungible, but it'll take me 1,000,000 years to crank out the tractable part. Sensible and fungible. So here, as to whether that is so, if we read him as saying sensible, he means sensible, fungible, and tractable. And then only meaning that that would suffice, and that's the necessary desiderata. Not that that's necessarily the only thing that would suffice in other desiderata of requirements about other things that happen to fulfill the same thing. But here, though, evaluating exactly that of a path measure on the space of all paths, this is about our measure theory. And so, just as we've been talking about a little bit about the Ramsey theory, Birkhoff, and then Lacuneri, quasi-invariant measure theory, topology, these are exactly the kind of ways that math, it says, okay, this balloon has got to stretch because we've just squeezed these parts of these domains to their fixed limits. They have been fixed. We have made it so that all our state assumptions are put, and we need somewhere else for this to give. And it's usually, well, let topology give. Or in the theory of functions, sometimes as well, let that function give. It's one reason why continuous domains are so hard, because first of all, we need to resolve everything with regards to often a formal apparatus about standard domain. And then we also have signal and line continuity, and they're standard in their domains. The fields is standards domain for this line, sweep, field, spray, and signal slide. That here, for example, then to go back to where the author left off, and he's been fair with his definitions, and he's cautious for us in the sense that he says and implies what's necessarily so and not necessarily so, and necessarily not so. That he says only by the formal definition of a path measure, that the formal definition of a path measure kind of lets out that measure has its own theory of things. On the space, with its own theory of things, of all paths. So he basically says that this path measure is what's underdefined. This measure must be defined consistently with the weighting factor of the exponentiated action, since that is a functional being integrated. That's the conditions. That's how it's arrived at this quantity fixing or making finite these values, as of in the series summation or arithmetic has what's agreed in the order of things is finite. To motivate this with a familiar example, it is recalled that the dt appearing in the Riemann sum of the exponential is an example of a type of measure called the Jordan measure and has the form tj plus 1 minus tj. So these are these infinitesimal measure elements. And so now I'm going to have to go look up again the Jordan measure, and I made a comment about it last time. About like, it's kind of like the Higgs field. It's not a real measure because it's in these infinitesimal line elements, so it's really a matter about the telescoping and what's so applied. But now I'll have to go look at the Jordan measure again. And it says, this is by no means the most general form of measure, even for the real line. Well, the most general form of measure has the non-measurable, but this is the iota values is a default form of measure, and as long as it's not bent, it's straight. This is by no means the most general form of measure, even for the real line. To demonstrate the relation between the function being integrated and the measure used to integrate it, one need only point out that the function qt, defined by 2.56, is not an integrable function using Jordan measure. That's the Dirichlet function, because that's the Dirichlet function was mentioned about the signal continuity. It's rationals and rationals, each dense. And so it would have different sigma algebras. That's all it is. Swanson would be well to have these notions provided for him. This is by no means the most general form of measure, even for the real line. To demonstrate the relation between the function being integrated and the measure used to integrate it, one need only point out that the function qt, defined by the Dirichlet function, is not an integrable function using Jordan measure. The Jordan measure must have sigma algebras, and they don't apply. If such a pathological function is to be rendered integrable, then a more general measure, referred to as Lebesgue measure, must be defined. And an attachment, and an apparatus, and a framing, and a coordinate space, preserving the affine, making a conformal mapping. ... The discussion of formal measure theory, and in particular the problem of defining measure of the space of paths, is very difficult and requires a level of mathematics well beyond the scope of this book. Well, less. However, some aspects of some inward paths can be made clear with a modicum of effort. One of the chief difficulties in constructing a rigorous measure for the continuum version of the path integral is the presence of the I in its definition. This is the Gaussian, this is the thing that he says, the oscillatory nature of the exponential creates difficulties, including unruly paths, i.e. non-differentiable and discontinuous paths. And that would include singularities and asymptotes and those that result as after kind of when we were discussing the meromorphic, there's not free analysis over those parts of the plane when the coordinate setting would result that it so happens that the method and the limit so built up would cause itself a discontinuity. Whether those are removable, this is kind of the meromorphic, that you can jump, you can make that gap without it skipping or ever scratching. But that it's not so is that it's being pointed out that all the standard methods since the 1950s, which everybody who got a mathematics degree would have had in their education, because they're generally very useful in all kinds of linear and classical things, and they're true, have that then in the system which involves more than one definition of continuity, that these are the things going on. And I'm glad now I have at least 3 definitions of continuity in my replete standard and extra standard analysis. Well, now I'm going to flip the ear tag, or what, the bookmark the other day, the folded over corner of the paper indicating a little place to catch and look, that we'll talk about this. So we didn't get into chapter 3, evaluating the path integral. There was a lot more interesting intuitive stuff in this here. So I'm going to put that down for a second. Now, yesterday we took a random look from the plain phone book with the Feynman lectures, and then I wanted to look up thermo and heat. Let's see what we got in here. Let's see what the introduction says. Richard P. Feynman, June 1963. He finishes up this introduction. I think, however, or it's Feynman's preface. There's a picture of him playing his bongo drum with a cheese-eating grin on his face. I think, however, that there isn't any solution to this problem of education other than to realize that the best teaching can be done only when there's a direct individual relationship between a student and a good teacher. a situation in which the student discusses the ideas, thinks about the things, and talks about the things. He's just teaching me. It's impossible to learn very much by simply sitting in a lecture or even by simply doing problems that are assigned. But in our modern times, we have so many students to teach that we have to try to find some substitute for the ideal. Perhaps my lectures can make some contribution. Perhaps in some small place where there are individual teachers and students, they may get some inspiration or some ideas from the lectures. Perhaps they'll have fun thinking them through or going on to develop some of the ideas further. Yeah, and then earlier he'd been talking about a quote from Gibbon: "The power of instruction is seldom of much efficacy except in those happy dispositions where it is almost superfluous." Now, I don't know about that, because instruction at least provides an excuse to sit down and let it sink in, the linear instruction development. Besides that, the autodidact automatically scans and incorporates into their comprehension everything on the page all the time. You know, from cereal boxes to this fine print, you know. The instruction is also a fair deal for everybody else. It's kind of like, you know, the difference between reading a movie and reading a book and watching a movie is that everybody watches the same movie, whereas everyone reads their own book. That there's something to be said for instruction, which can otherwise be a big waste of time when it's either wrong or not absorbed or not relayed correctly or read into deadpan of voice. So anyways, that's something. But these lecture notes is basically its own little dictionary and its own little encyclopedia of all these concepts in physics. It's a little encyclopedia of space-time, rotation, 2 dimensions, geometrical optics. Now this is something we talked about, was the geometrical optics and optical optics. That the photon travels in a line, but then the light is exactly about the straightest line you can find, because this propagation in free space is exactly in a direction. See, that is bent according to the propagation of the medium, or whether it's refracted. And we talk about reflection or refraction, that I often mispronounce reflection, but mean refraction. Whereas when I say gravity and gravity, I mean the gravitic and the gravific, which are 2 different things. But so when he talks about geometrical optics, there's geometrical paths, which are linear and reflect angle incidence. And then there's optical paths, which focus, which are brought in as to a point, or as off a point, and make the aura, this kind of thing. The previous section is optics, the principle of least time. And so the principle of least time is kind of like the principle of least action. It's that nature is efficient. And for the ubiquitous success of mathematics, that yes, a straight line is the shortest distance. For all these paths in the path integral, it results that, however, according to the mechanics of the action, that line is straight. That's what it's computing is what is the mechanics of the action. But another way to look at it is like, well, once you measured it, then that's how the line was straight. And so that's a path through the space. Radiation damping. And yeah, so this is a cool little thing, and it does remind me again of the mathematics, or the Encyclopedia of Mathematics that Eric Weinstein put together a long time ago, and then that got consumed by Wolfram, and now it's their encyclopedia. And so anyways, this is more about the path integrals. We made about half a page in Swanson's book, and we got talking about why line continuity, or Jordan measure, and signal continuity, or Dirichlet function, are so relevant. What's otherwise continuum analysis as follows: this setup of the complex and the Gaussian, which makes for these linearizations and what comes in and out of linearizations and small angle approximation, which I learned about in a physics course in college. That then, as he's going along helping explain the setup about these inner and outer products, and about the degenerate and the detailed, and the defined and the derived, how it can work at both axiomatics and reverse mathematics of a sort, finding the least model necessary. We also talked about the uniqueness of solutions and lack thereof, and the requirements and desiderata of these matters of style, and kind of how much an iceberg of style a simple word can be that admits more than one definition, or is introduced when it could be left out. These kinds of things. Anyways, I hope you have a great day. This will go in the path integral talks, and there'll be more of them later, because there's still about 2/3 of the book to go. But at least we'd have a way to start from the beginning. All right. Good afternoon.